Okay, forces and motion. Hope everyone's doing okay this morning. Can everyone hear me? Okay. So last time we talked a little about forces and motion. We described acceleration. So does anyone remember what the equation is for acceleration? So we have change in velocity over time. So this could be starting, this could be stopping. So starting would be speeding up, going from 0 to some velocity, slowing down, going from some velocity to 0. This can also be a change in direction. So we know that velocity is a speed with direction. So changing direction is going to change acceleration. So let's talk a little bit about unbalanced forces. When you have a balanced force, the object is either not moving or it's moving at a constant speed. So if there is a constant speed, we have no acceleration. So say you have a rock and the force between it and the ground, the friction, is applying pressure this way, and there's some pressure this way. This is not moving. If these are equal, this is not moving. So that would be no acceleration. But if you have an unbalanced force, where you're pushing really hard on this, and then there's only a little bit over here, you're going to have it moving this way. It's going to change in speed, and it's going to have some form of acceleration. So deceleration. So we know that acceleration is change in velocity. Again, this triangle right here just means change in velocity over time. So what's change in velocity? Change in velocity is your final velocity, which we write as vf minus vi over time. So if something is slowing down, its final velocity, let's say, is 0. Say a car is stopping. So say it's going 40 kilometers per hour, and it's slowing down to 0. So we'd have 40. So it's going 40. And let's say it takes it 5 seconds to stop. So we have, oh, I'm sorry, let's see, we have 0 is its final, because it's stopping, minus 40. Okay, and this takes 5 seconds. Okay, then we're left with negative 40 over 5. So the answer would be 7. So 7 kilometers per hour per second. Negative. This is a negative number. So the negative will carry over, and you'll get negative 7 kilometers per hour per second. And you know that this negative number just tells you that it's slowing down. So if you see an acceleration, that's an A, by the way. If you see an acceleration and you see this negative number, it just means that the object is slowing down. Hopefully that makes sense. Oh yeah, I'll just put this in here. Feel free to email me if you have any questions about any of these slides, and I'll be happy to answer any questions. So yeah, just so you know, if you see a negative number, then it means you're slowing down. If it's positive, it means you're speeding up. So speed, talked about this last time. A way to describe motion. So average speed would be distance over time. So you just, we did this last time, distance over time. So before we did acceleration, which is velocity, this is speed, which is different. This is speed is just the distance, so this could be in meters and this could be in seconds. So just what we use for distance is the meter or the kilometer or the millimeter, and time is seconds or hours. The average speed, so say you're plotting a graph and over here you have distance, okay, distance, and you have time, and say this is like 4 hours and this is 400 kilometers, and you're driving. You're going to be, if you're in traffic, you're going to be stopping and starting. So your graph's kind of going to look like, you know, like that. This is not a constant speed. You're moving up, you're going down, you're moving up, you're going down, and what you want when you do these equations to find speed is you find the average speed. So you would take the total distance, which in this case would be 400, and over the total time, which would be 4 hours. Okay, so then your line would look more like this. And when you see a straight line, this means constant speed. And this is more like what in real life you start and you stop, and this would be the normal graphed speed, and then you just take the average and it creates a line like this, which is kind of basically the sum of all your slowing up and slowing down and starting up. So yeah, speed that does not change is a constant speed. So this is a speed and it's not changing. It's the same distance over time. It's just increasing at this steady slope. Instantaneous speed. So if you have, again, this this normal graph, if you pick a point here, you can calculate the distance over time. So at one specific point on the graph, you have your instantaneous speed. So these are three different types of speed. The first is described by a straight line, and the second is, or I'm sorry, the first is just the total. So you could write it as R equals dt over t. This would be RA is average speed. Okay, so this is very, very clear. It's very straightforward. S is the same. In this case, we'll say S is R. Okay. Big S and little r. I was using little r, but let's use, and this is the same as little d. Okay, so these are the same and these are the same. So speed equals distance divided by time. Average speed is the total distance over the total time. Okay. Okay, so this is just a really simple example problem. So we have a football field is 100 meters long, and it takes a person 20 seconds to run its length. How fast was the football player running? So we have the distance is 100 meters, and the time is 20 seconds. So can anyone tell me, so we have speed equals distance over time. How fast? This means speed. So we have 100 meters. Yes, perfect. 5. You don't need any question marks at all because that is totally correct. 20 seconds equals 5. So can you give me the units for 5? What are the units? What am I going to write here? Oh, yes, yes, it is. So can anyone describe to me the units for speed? So we're talking about just distance over time. Meters per second. Perfect. Thank you. So yeah, you divide by 20, it equals 5, and this would be meters per second, which is usually what you see for speed. You know, with a car, you'd see kilometers per hour, but a lot of times in physics, they use meters per second, depending on how large the number is. Okay, so this is just a very simplified version. This is exactly what we just did. Distance over time, this is divided by, same thing, distance over time, 100 meters divided by 20 seconds, 5 meters per second. Remember to include the units, which you did very well. Okay, so balanced forces. So I talked a little bit about this. When all the forces acting on an object balance each other. So without going into too much detail, we have a rock sitting on the ground. There are several forces acting on the rock even though it's not moving. We have, say, some wind acting on it this way. You know, wind. We have the resistance from the wind. So this is the wind, and this is the rock. Kind of, it's too heavy to be moved by the wind, so it's pushing back. It's pushing back. We have the weight of the rock. Okay, it's pushing down on the ground, and it's not going through the ground. So the ground is exerting some force on the object. Okay, so see all these arrows. If the object is not moving, if this rock, very exciting, I know, rock, so we know that if it's not moving, the forces are all balanced, so that these forces are still here, and we can do various things to measure the forces. But right now we've got wind, we've got the resistance to the wind, we've got gravity, and we've got this force that's pushing back on the rock that's keeping it from sinking. Okay, so this would be considered a balanced force. Balanced forces do not cause a change in motion. So, like I said, this rock is not moving. So, friction. Friction is very important. It exists almost everywhere. It's a force that resists motion between two touching surfaces. So, you know, take a look at anything. When you kind of slide, or when a car is driving, the wheels are touching the road. You know, the road, say the car, beautiful monster truck car here is traveling this way. The friction is going to be the force pushing this way. Okay? And if the car is moving this way, it's actually this value is much larger. It's going this way with much more force, but there is still force pushing on the car. It's keeping the car from moving, and that's called friction. So if there was no friction, the car would be able to move much more easily along the road. But since it's touching another surface, there's going to be a force acting against the movement of the car, and we call that friction. So it says here, acts in the opposite direction of the object's motion. So whatever direction the object's moving, friction is going to be an opposing force, meaning that it goes in the opposite direction. It's very important. You can apply this to many things, bicycle, any sort of object that's moving while touching another force, or any object that, say you have a rock, again, we'll use our rock, and it's on the side of a hill. Okay? So gravity wants to pull it down the hill. But you know, you've seen rocks on hills, they're not all moving. So if they're not moving, there is an equal force holding it onto the hill. And that force is friction. Okay? So if this is confusing, don't worry about it. We can review these slides whenever you want. But basically, friction, just know that it's the opposing force that happens when two surfaces touch each other. So this rock's not moving. This is a balanced force, friction holding the rock onto the hill, and gravity that's trying to pull it down. And when there is friction, say in the car example, which is the opposing force for this motion, there's heat produced. And the more friction there is, the more heat that's produced. You can use your hands, and if you go like this, that creates heat on your hands. That's friction. Two moving, touching surfaces, heat is produced. You can see it just by doing that with your hands. Okay, inertia. Inertia is really cool. It says moving objects tend to continue moving unless acted upon by an unbalanced force. So this is another example of a balanced force. It can still be balanced if it's moving. Say an object is traveling through space. Okay, this is our rock in space. It's going to continue moving if all the forces are balanced and it's moving. So there's like, you know, it's just going to continue moving at the same speed. There's going to be no acceleration. It's just going to continue moving forever. Objects at rest tend to stay at rest unless acted upon by an unbalanced force. So just like the rock, if it's not moving, it will continue to not move unless another force acts on it. So we have the rock, and say there's a gigantic gust of wind, you know, like in a storm. It's going to blow this rock that wasn't moving. It's going to blow it that way. It's going to move. But this is an unbalanced force. You have this little bit of resistance that we had before, but it's overcome by the wind. And the more mass an object has, the more inertia it has. So the bigger an object, the harder it is to start or stop moving. So I don't know if any of you are familiar with any major football players, but giant people that are running at full speed are really hard to stop. Or if you have a giant rock that's rolling down a hill, it's the bigger it is, the harder it is to stop. If it's a little pebble, small rock, it's very easy to stop. But if it's a gigantic rock, you probably want to get out of the way, because it's going to be really hard to stop. And that's kind of the concept behind inertia. This is kind of the the technical description, it says more massive objects, which is just bigger objects with more mass, not necessarily bigger, but you can think about it that way, are harder to start moving and stop moving. Smaller objects are easier to start and stop moving. So like I said, if you have a gigantic boulder, it's going to take more force to move it than if you have a little boulder. It's just going to take a little bit of force. Okay, and this is kind of the concept behind inertia. So Newton, who about 300 years ago was, he's a physicist and really brilliant guy. He came up with these laws, and they're kind of the basis for general physics. And his first law, it talks about inertia, and it says an object at rest or in constant motion is acted upon by balanced forces. An unbalanced force will change the motion. So it basically means if you have something that is at rest, which means not moving, this just means not moving. Okay, so if this object is at rest or in constant motion, it's being acted upon by balanced forces. So just like the rock, the forces will be equal. That's the key. So you have the rock with the wind, the resistance to the wind, gravity, and the force acting on it. These are all forces. If you took away the resistance, if you took this away, the object would move this way. But since it's there, the object stays the same. If you took away gravity, okay, if you took away gravity, the object would start floating in the air. Okay, and the same is with all these arrows. If you were to remove one, the object would start moving, but only because there are these equal forces acting upon this that it can stay still. And the same goes for an object that's moving and has no acceleration. So say we have an object, this rock is in space, and it's moving. All these forces, if we're in space, there aren't any other forces. This thing is just moving, and so these forces all equal 0, and they're also balanced, but the object is moving. This is a little bit harder to understand, but you can think about it with the terms of at rest. This is what Newton meant by this. And he also said in this first law, acceleration of an object at rest or in constant motion is 0 meters per second, which is just a really fancy way of saying there is no acceleration. So Newton's first law, A equals 0. This is really important. So if we're talking about Newton's first law, he is assuming A is equal to 0. There can be no acceleration for this to work. So and in the second part he says an unbalanced force will change the motion. That means this is where acceleration comes in. So A equals 0 for this first part, and then after this, A is greater than or less than 0. So you could have negative or positive A, but A does not equal 0. So let me write that a different way actually. A does not, this just means does not equal. So for this first part, A has to equal 0. For the second part, A does not equal 0. So that's just what this is saying here. Okay, so first law of motion. I don't know if you can observe the link. They can observe it. Can I observe it? Okay, so this link is basically uh, a video of a football game, and it's got a guy throwing a football. You can just copy and paste this into your web browser, and it will show you this very short video. Um, don't pay attention to this bottom part. Yeah, this is just a classic example of how physics is everywhere in life. And if you go out and play soccer or football or badminton or whatever, inertia is always going to be there. Newton's going to be there all the time, so he's going to be hanging out the whole time. And this is just a classic example. If you want to think about it, watch this video and then think about Newton's first law, like what object is at rest at the beginning, and what are the forces that are acting on the object. So in this case of the video, it's a football, and we want to think about is it at rest? Is it moving? Is it moving at a constant speed? I got a little pop-up here. I'm not sure what it means. Okay. Okay, so hopefully this gives you a little insight as to how this kind of law can be used in real life. So Newton had several laws. He had three main laws. His second law describes motion created by unbalanced forces. So now we're talking about unbalanced forces. So A does not equal 0. Okay? Why does it keep going back? A does not equal 0 in an unbalanced force. Mass and acceleration change in opposite ways. The more mass an object has, the more force it will take to accelerate the object, the slower it accelerates. So we have this equation, famous equation used all the time. It's called force equals mass times acceleration. When you have just two letters next to each other, it's the same as m times a, or you could have m times a. This is just kind of how people in physics tend to write it. F equals ma. It's just, you kind of know that it means multiply. Okay, so this just means that it's linked with inertia as well. So if you have a huge number here, say 5 kilotons or something, and then you have the force is, say, like 3 newtons. Newton is the unit that we use for force. So if we know this, well, let me use it. So from general math, okay, we know that if this number is really big, if we know force, if we know this number is going to be really big, then this number is going to be really small. And if this number is really big, then this number is going to be really small. If we want to get the same equal. So if you increase mass, so say we have force is equal to 10. Okay? And mass is equal to 5. A is going to equal 2. So this would be 2 meters per second squared, or whatever the unit, whatever you want to say, but this is going to be 2. So if you were to increase m, okay, you get a heavier object, something that's twice as heavy. Say it equals 10. Then a is only going to equal 1. It's not going to equal 2. So this value is going to go down if this value goes up, and vice versa. So the less mass an object has, the less force it will take to accelerate the object. The faster it will accelerate. So hopefully this kind of makes sense. So I can write it a different way. In F equals m a. Again, I'm sorry about the pen here. If we had a whiteboard, I could do this much faster, but just kind of bear with me right now. F equals ma if m is really big. If m goes up, a goes down. Okay? And if m goes down, a goes up. Okay, so these are inverse, but you don't need to know that. Just if you want to read this over, you can, but hopefully this makes a little bit more sense. If you increase mass, it's slower, the acceleration goes down. If you decrease the mass, it's faster, the acceleration goes up. This is another video. This kind of shows the second law of motion. It's another football drill. I didn't pick these videos, so if you are confused, don't blame me. But basically this is showing us that if something is bigger and heavier, it's harder to move. So that is really the simplest way to understand it. If you try to use one person to move a small pebble, it's very easy, and if you try to use one person to move a giant rock, it's very hard. Okay, so again, if this is confusing, you can go back and review the slides or send me an email. I'd be happy to answer your questions. So the third law of motion, it kind of, all these laws are very connected, describes why forces act in pairs. For every action, there's an equal and opposite reaction. This is the main phrase. Action and reaction forces are equal forces acting in opposite directions on different objects. Okay, so let's go back to the really thrilling and exciting rock. So like I said, you have the resistance. So we could use a different example and say this is a rock at the bottom of a river. This is the water. Okay, it's pushing on the rock. The rock is not moving, so there's this resistance. Okay, and that's caused by its mass. So this force is not big enough mass, is not big enough to accelerate this object because it's so big. And then you have gravity, and then you have resistance by this rock bottom. This is the bottom of the river. So each of these forces are completely equal if this thing is not moving. So for every action, in this case the water, the resistance of the water is exactly the same, is equal. Okay, if you really want a good example in front of you, you can take your hand and put it down on your desk, and you won't be able to push your hand through the desk, because the harder you push on the desk, the harder the desk will push back on your hand. Okay, and it sounds crazy, but it's true that as you press harder, the desk is actually resisting more, and the resistance is completely equal to the force you're using to try to push through the table. But since we're not strong enough to go through the table, hopefully you're not breaking all your desks, but yeah, this is a perfect example of Newton's third law, and you can find it anywhere. Um, and just if that doesn't make sense, then there's another video here, which is a baseball video, and it will basically show you that as the baseball is pitched, the batter is hitting it, and the two objects, the object is meeting an equal force, and the ball keeps going. So you have this equal and opposing reaction. So yeah, think about the desk, or there's plenty of things. Also, if you are just standing or walking, as you walk, your weight pushes on the ground or the asphalt, and you don't sink down. You don't sink into the middle of the earth. You have this resistance that comes from the bottom and holds you up on the road, and that is the force pushing up on your foot as your foot is pushing down. And those are completely equal. If the road was pushing you harder than you were pushing it, you'd go flying into the air. And if you were pushing harder than it was resisting, you would sink down into the road. Okay, this is very simple. We talked a little bit about this before. Speed is distance over time. Okay, velocity is distance over time plus a direction. So the only difference is that velocity tells you a direction. It should say distance, time, and direction. Speed is just distance and time. So if you hear the car was traveling 20 kilometers per hour, which is really slow, to the west. Can someone tell me what that is? That speed or velocity? So it's velocity because you're given the direction. So direction can be down, up, left, right, north, south, east, west, southwest, whatever you want. It's you guys know what direction is. Speed will just not have a direction. And this is an important difference because when you're talking about real life, if you do these equations and you call something speed, if you have the speed, you can't talk about acceleration because acceleration is velocity over time. It's not speed over time. It's the change in velocity over time. So you need to have the direction in order to find acceleration. So this is important. How can force affect objects? Okay, so how can forces affect objects? Like we said at the beginning, it can slow them down, speed them up, stop, start. Okay, what is this? What does this relate to most that we just talked about? Something that involves how big the object is, how much mass the object has. What is the force to slow them down, to speed them up? What's the force to start an object? Can someone tell me what equation you would use to find how much force you would need to start an object or to stop an object? No? I mean, I could keep repeating it, but it seems like I'm repeating it a lot. It's F equals ma, right? So if you have this object with a certain mass, and you know that its acceleration, you can find out how much force you'd need. How much force is it exerting? You know this, and that's how you find out how much force you need to stop something or how much force you need to stop it. And if this value, mass, is bigger, that means that the force will be larger to start or to stop them, and that's what inertia is. So hopefully maybe you should review the inertia section and you understand this, or email me. But yeah, this is just, most of this you could find from MA. F equals MA. Okay, so can someone tell me what this graph shows? What's going on here? So this is time. Let's say this is 4 seconds, and this is distance here, and this is, say, 2 meters. So distance is not changing, it's staying at 2, and time is increasing from 0 to 4 seconds. Can anyone tell me what this is portraying? Do you remember the rock? No. Okay, this is basically something that's not moving. An object which is not moving or at rest. Time is going by 1, 2, 3, 4, and the distance is not changing. So say you're over here at 0, this is 2 meters, and 1, 2, 3, 4. There's no change at all. So distance stays the same as time goes by because it's not moving. Pretty simple. This is distance over time. So again, we're talking about speed. We don't know the direction, so this is not velocity, this is speed. We have distance over time. Can anyone tell me what this is? It's straight, so we know that the slope is constant. That's a hint. Constant. Can anyone tell me what this graph is showing? We talked about it earlier. Okay, so this is constant speed. This is wrong. It should be speed. The graph shows that the object's distance increases as time passes. So the object is moving, and if we knew the direction, it would be velocity, but since we don't, this is speed. So constant speed. Okay, so this one's a little bit trickier. Can anyone tell me what's going on here? So we have distance is changing, right? So say this is 6 meters, and this is 2 meters, and this is time. This is 3.5 seconds. Distance is changing, time is changing, and the line is straight. Any ideas? So like we said before, this is just speed is decreasing. No, this is, I'm sorry, this is a constant speed, but this is constantly moving. It's just moving from away from you to towards you. So say something is 6 meters away and it moves to 2 meters away, it's still moving at a constant speed, because the line is straight. If the line was, like this, you would be able to find the average speed by taking the total time, total distance, and dividing it by the total time. And you'd get a line just like this if you were to graph it on a calculator or in your book. Okay, so this is pretty interesting. Distance over time, but you have kind of the slope is changing. This is a little bit different. Slope is changing. The line is no longer straight. You still have distance and time. So this is what acceleration is. This is the change in distance over time. So we have distance over time, which is velocity if you have the direction, and then you have this time is changing. So to measure the time, this time that's changing, you have acceleration. Can anyone tell me the meaning of this graph? It's got three kind of different sections to it, all of which we've talked about. So distance over time, so we're still talking about speed, or if we knew the direction, we'd be talking about velocity. And so say this is 0 meters, and this is 3 meters. Okay? This object is going from 0 meters to 3 meters. Say this is 1 second. Say this is 3. And this is 5. So from 0 to 1, what's happening here? The line is straight. From 0 to 1, this is constant speed. From 1 to 3, we have distance is not changing, but time is changing, so we know that that's an object at rest. And then we have from 3 to 5 is the object is now coming towards you. Say you're at 0, the object is coming towards you from 3 meters, and from 3 to 5. So this would be kind of like a yo-yo. So the object is going away from you to 3 meters, it's kind of hanging out there, and then it's coming back down to you, back to you. So this would be just like a yo-yo. Constant velocity, object is at rest, and it's also moving at a constant velocity, but it's just moving back towards you. So don't be confused about this graph, because we know that this y-axis has now changed from distance to velocity. So we have meters per second over seconds. So if you remember from the last lecture or from the beginning of this lecture, we talked about what uses the units, meters per second per second. So this would be the same as the change in velocity over time, which is acceleration. Meters per second squared. Okay. Constant velocity. So acceleration here, there is no acceleration. It's at constant velocity. But when you have velocity over time, this is a graph that you'd use to show acceleration. So what's here? This is kind of similar to constant speed, but instead we're using meters per second per second. It's constant. It is accelerating. So the speed is increasing, the velocity is increasing over time. So say this would be 0, 50, 100. Say this was 1 and 2. So if we were using this for maybe to talk about a car that was accelerating, we'd maybe be doing, so this car is pretty fast, 50 meters per second in 1 second. So after 1 second goes by, it goes from 0 to 50 meters per second. Then as another second goes by, it goes to 100 meters per second. So this would be a perfect way of talking about how fast of acceleration a car has. We know that because the line is straight, acceleration is constant. So if you want something to think about for later, you could say what speed is this car going to be going after 4 seconds? How fast is it going to be going after 4 seconds? So if you want to... Yeah, perfect. 200. You got it. So yeah, and it, if it was 8 seconds... So every second it's going up by 50 meters per second. After 8 seconds, so it'd just be 400 meters per second. It'd be double. So it's because this is constant. And 800 meters per second is, yeah, 400, perfect. 400 meters per second is really fast. Really, really fast. This would be a very, very expensive car. Hopefully one day I'll be able to afford one, but not today. So yeah, that's all there is for today on this lecture. If you have questions about any of this at all, I know it can be confusing. We'll revisit anything you have questions about, in class later. Just feel free to ask questions. Yeah, okay, so if you missed the videos yeah, that are on the PowerPoint, you can, where are you going to post them? Okay, yeah, you can find them on the website, or you can just take the PowerPoint and copy and paste it into your web browser. So hopefully, they're only a few seconds long, the videos, but it's a good way to kind of learn Newton's laws and how they apply in real life. Okay, so have a good one. See you some other time. Bye.